Welcome back to the deep dive. If you've ever had to sort through a huge volume of unstructured text, think hundreds of legal contracts or thousands of field notes, you know the pain point. All this valuable knowledge is just trapped.
It's the exact same story in medicine, only the stakes are, so much higher. The medical world generates just an astonishing amount of data every single day.
Right.
But the most critical diagnostic information, it's often buried deep inside these unstructured free text reports, especially in things like radiology notes.
And we've been hearing about this information revolution in radiology for what feels like 2 decades now, but it always seems to stall out at the same place.
At the reports themselves.
Exactly. We don't have scalable, flexible tools to actually read and understand what humans have written. If you want to do a large-scale review, say, to see if an expensive MRI was used appropriately, you still have to have human radiologists manually read every single report. It's just so slow.
It's slow, it's expensive, and frankly, it's a bottleneck that can cost lives and money. And, well, that's our mission for today's deep dive. We're looking at a study that really tackled this problem head on.
They asked a pretty groundbreaking question, right?
They did. They asked, can an open source, privacy-preserving large language model, and this is a key part, one that hasn't been specifically trained for medical tasks, can it automate the extraction of critical diagnostic info from thousands of real, messy radiology reports with genuine accuracy?
And this is so compelling because the researchers, they didn't pick an easy test case. They went straight for a really complex clinical context. Emergency brain MRI reports for patients presenting with headaches.
Which is one of the most frequent and complex issues you see in an emergency department.
Sure. Trying to figure out if it's a routine headache or a neurological emergency is incredibly tough. And reviewing that data to improve care means sifting through a huge, chaotic data set.
The need for this is just immense. If you can unlock that data, you can refine guidelines, you can improve patient safety, you can cut down on unnecessary imaging. But the challenge, both technical and ethical, has always been the same.
How do you let a powerful AI read sensitive patient data without, violating confidentiality?
That's right.
Okay, so that's the tension. Let's unpack the solution they found. The researchers didn't go for the biggest commercial AI. They chose an open source model called Vicuna.
Well, before we even get to Vicuna, it's worth looking at the established landscape.
Okay.
If you wanted to do this before, you were basically stuck with what we call rigid solutions. So rule-based systems that needed these really precise dictionaries for a specific language or even a specific hospital.
Or those BERT-based models that needed tedious fine-tuning every time you wanted to ask a new question.
Right. The inflexibility was the enemy.
Yeah. So everyone knows the big commercial names, right? GPT-4, Gemini, they have fantastic language skills. They're flexible. Why did the researchers just use one of those?
And that is the critical paradox of medical AI. These commercial cloud-based LLMs, they show amazing performance on general tasks, but they live in the cloud.
Managed by third parties.
Exactly. So sending sensitive, real-life patient data that's covered by strict laws like IHE to a third-party server is just a non-starter.
I see. So a lot of those previous studies on medical LLMs weren't even using real data.
Many of them had to use highly sanitized or sometimes completely fictitious reports just to get around that security issue. You're not testing AI in the real world if the data isn't real.
That's a huge distinction. So the breakthrough here isn't just the model itself, but where they ran it.
Precisely. They used Vicuna, which is an open source model based on Meta's Llama architecture, specifically because it could be run on premises.
Meaning locally, within the hospital's own secure systems.
Exactly. In this case, on 2 off-the-shelf NVIDIA GPUs, the medical data never, ever left the building. This is the crucial step for actually deploying AI in a real clinic. It changes the question from can AI read this data to can AI read this data safely?
And they didn't use some small, clean data set to test this. They went for volume and complexity.
They did. They took 2,398 consecutive emergency brain MRI reports from a large French quaternary center, CHU Lille, over a full year.
Wow.
And here's a detail I find fascinating. Not only was the data real-world and messy, generated by 43 different radiologists and trainees.
So huge variability in writing style.
Huge. But on top of that, the reports themselves were originally written in free text French.
Wait, the reports were in French. How did Vicuna process them? Did they have to translate everything first?
No, and that's the genius of using a modern LLM. The research team wrote their prompts, their instructions for what to extract in English.
No way.
Yes. The Vicuna model had to simultaneously translate the French medical text, understand the complex clinical ideas inside it, and then extract the information based on the English instructions.
That's incredible. The fact that it worked well just shows an amazing robustness that older, rigid models could never, ever match.
It's a huge lift for an off-the-shelf model.
Okay, so Vicuna is secure. It's linguistically robust. The researchers then gave it 4 distinct jobs to do. Let's start with the feature extraction tasks, the sort of low-hanging fruit.
Right, the first 3 tasks were about pulling out fundamental facts. It sounds simple, but for a human, it's incredibly tedious.
So what were they?
Task 1 was just detecting whether headache was mentioned as a symptom. Task 2 was detecting if a contract medium injection was performed, which is critical. And Task 3 was simply classifying the final conclusion as either normal or abnormal.
These are the high-volume, low-expertise jobs that just eat up human time. So if the model is good at this, the time savings would be massive. But how good was it? I mean, good in medicine has to be near perfect.
And Vicuna achieved what the study called excellent accuracy across all 3. And I have to stress this. The model had 0 specific fine-tuning or training on these reports. It was just using its out-of-the-box knowledge.
Let's focus on task 1, finding the headache symptom. Give us the metrics, but maybe frame them against the human cost.
Okay. For detecting headache, Vicuna hit 99.0% accuracy. The machine processed all 2,398 reports for that single task in 3 hours.
3 hours, okay.
Now consider the human side. The researchers calculated it took human radiologists about 180 to 210 minutes.
So 3 to 3.5 hours.
Exactly. To manually review the reports for just that single task.
So in the time it takes one human to do the job once, the machine did the job more than 2,000 times with 99% accuracy. It's not just efficiency, that's a whole paradigm shift in how you can review data.
Absolutely. The machine finished the entire triage for almost 2,400 patients in the time a human would just be getting started. And task 2, finding the contrast injection, was 99.3% accurate, and the normal-abnormal classification was 97.8%.
So that confirms it. For standard feature extraction from messy, unstructured medical text, an on-premise, open-source LLM isn't just viable, it's a game changer. It can handle synonyms, misspellings, negations, all of it.
And the clinical reality shows why this speed is needed. The manual review showed that about a quarter of those emergency MRIs were for headache, and about 38% of those had an abnormal finding. Automated triaging saves massive amounts of time.
Okay, very impressive scores for feature extraction. But now we get to the really hard part. The ultimate test in radiology isn't just, is it there or not? It's causal inference. It's connecting the dots.
Precisely. And that was task 4, and it was, by a wide margin, the most difficult. The LLM was asked to figure out if the main abnormal finding could certainly or probably explain the patient's headache.
Hold on. If even human experts might not fully agree on that, because it's an interpretation, right? How can you possibly expect an off-the-shelf LLM to get that kind of subtlety?
That's the heart of the challenge. This wasn't a checklist. Causal inference means you have to appreciate the descriptive language adjectives about size, shape, signal. There was no predefined list of pathologies to look for.
And the humans themselves didn't perfectly agree.
Not at all. 4 radiologists reviewed the reports, and their inter-rater agreement, a statistic that measures how much they agree, was only 0.77. That's considered substantial, but it is far from perfect consensus.
Okay, so how did this task-agnostic LLM do on a job that even highly trained humans found tricky?
Its overall performance on the causal task was 81.9% accuracy. Its sensitivity was actually quite good at 88.2%, so it was good at finding a headache-causing lesion. But its specificity, saying a lesion was not the cause, was a bit lower at 73.0%.
82% accuracy on a complex objective task is still pretty remarkable, especially when the human baseline isn't even 100%. Did they find any link between the LLM's performance and how much the humans agreed?
This was the real aha moment. The LM basically mirrored the human consensus. On the reports where the human raters all agreed, Vicuna's accuracy shot up to 89.7%.
Wow.
But on the reports where the humans were less certain, where the original text was probably more ambiguous, Vicuna's accuracy dropped to 73.9%.
That's so critical. It means the LLM isn't just making things up. It's struggling when the source material itself is ambiguous. It's actually highlighting the ambiguity in the human reports.
Exactly. It's a tool that can assess the clarity of the input, not just the content.
Okay, but in a clinic, trust is everything. If the AI makes a mistake, you have to know why. Did they look into explainability? Could Vicuna, self-audit?
It got really good at it, actually. The researchers would use follow-up prompts, asking it to reflect on your answer and detail it. And Vicuna would frequently provide self-explanations or even self-corrections.
Give me a concrete example. What does that self-correction actually look like?
It was almost like it was saying, my bad, I misunderstood. For example, if it got the contrast injection wrong, the follow-up might say something like, apologies, upon review, I see the term without iodine was used. My previous extraction was erroneous, as I misread contrast mention for contrast performed.
So it could tell the difference between the discussion of contrast and the actual procedure.
Yes. That transparency, that ability to articulate its own error, is vital for building clinical trust. It moves us way beyond a black box system.
What about the actual medical errors it made on that causal task?
They were scattered. For false positives, it often marked things like small incidental aneurysms as causing the headache, even when the radiologist didn't. For false negatives, it missed two pretty serious findings. But the key thing was there was no single systematic error pattern. The failures were decentralized, which suggests the model is generally quite robust.
So let's recap where we are. We have an open source model running locally, getting near perfect accuracy on feature extraction, and doing remarkably well on complex causal inference. This has to be a huge strategic advantage. What are the key takeaways here?
They really revolve around mitigating risk and increasing access. So first, data privacy is solved. There is zero communication of medical data to external servers. Second, you get reproducibility. You know the model version, so you can do version control, you can monitor from model trip.
Which is essential for quality assurance in a hospital.
Absolutely. And the third and fourth points are what make this accessible to so many more places around the world.
Okay.
Third is cost. Once you have the hardware, there's no extra cost that scales with how much text you process, unlike the expensive commercial models. And fourth is flexibility. Because it's a public, task-agnostic model, the method can be easily adapted to new data, different hospitals, different languages, without some massive, expensive setup.
And that flexibility, that opens the door to using these LLMs not as replacements, but as powerful assistants for those low expertise, high volume tasks all over the hospital.
For sure. Think about a radiologist's daily work. The LLM could be scanning prior exams instantly, pulling out details for follow-up notes, maybe drafting the bulk of a simple report, or even just running a quality check on readability before it's sent out.
And for the clinicians ordering the scans,
The LLM could annotate or structure the report, making the key findings much more digestible and searchable.
this also solves one of the biggest problems in computer vision AI, which is data scarcity.
That's a key loop closure for AI research. High-quality, manually labeled data is incredibly expensive to create. But by leveraging the expert information already in the radiologist's free text report, these LLMs can generate high-quality labeled data automatically.
And that data can then be used to train specialized computer vision models.
Exactly. It could dramatically boost research and development of new diagnostic tools at a fraction of the cost. It's an information multiplier effect.
So this deep dive really provides strong proof of concept. Open source LLMs can handle high-stakes information extraction from messy, real-life medical text with excellent accuracy, all while protecting privacy and keeping costs down.
And here's the provocative thought to end on. The model they used here, Vicuna version 1.3, is already outdated technology. Newer, better open source models like Llama 2 and its successors are already out there. So if an older, task-agnostic model can perform this well on subjective causal inference and get near-perfect scores on critical extraction tasks, what new horizon does this open for the speed, safety, and democratization of data analysis, especially for global health systems that can't afford proprietary cloud services?
It makes you wonder what other fields that rely on complex, unstructured free text, I'm thinking patent law, deep engineering logs, historical archives, what they could do right now by shifting to this powerful, private, locally run approach. That's a deep dive for another day. We'll talk to you next time.